Okay, so the last case of partial fraction expansion is for a Laplace transform that has complex conjugate poles. And I wrote this like this before. Numerator of S over S plus P1 times, and the way I wrote it, I guess, was S plus sigma minus j omega times S plus sigma plus j omega. Okay, and I'm going to rewrite that one other slightly different way. So it turns out we have the poles here, S equals minus P1 and minus sigma plus or minus j omega. Okay. Now one thing, if you remember when I talked about the cosine, a pure cosine just had the imaginary part, right? The pure cosine had poles at plus or minus j omega, and there was no real part there. And if we go all the way back to the beginning where I was talking about poles and what they look like, so I plotted the S-plane here, the real part and the imaginary part, and I said when I have a real pole here, like a pole at minus a, or in other words, corresponding to a Laplace transform that looks like 1 over s plus a, that corresponds to a decaying exponential of the time domain. And then when I have purely imaginary complex conjugate poles, those correspond to a oscillating cosine. It's just oscillating all the time. Or it could be a sine or a cosine. Now it turns out if I have a pole pair that's over here, let's say just someplace like this, some pole pair like this at minus sigma plus j omega, and erase this guy, minus sigma minus j omega. Well, it combines these two characteristics, right? So we've got an oscillatory part and a decaying part. And so erase this guy here. So what this looks like in the time domain, it's oscillating and decaying downwards. And so this is going to be e to the minus sigma t cosine omega t. Okay? So the real part is the decay envelope, and the imaginary part is the oscillation frequency. Okay? So let's go back to this partial fraction expansion. It looks like this. Now I'm going to write it one slightly different way. Numerator polynomial over s plus p1, and I multiplied this out. S plus sigma squared plus omega squared. Okay, so when I multiply the complex conjugate terms together, I get this: s plus sigma quantity squared plus omega squared. Okay, and the reason why I've written it this way is that we can then expand it like this, r1 over s plus p1, right? So there's a simple one, r2 s plus r3 like that, over s plus sigma squared plus omega squared. And the reason why I've written it this way is because there is a Laplace transform that looks like this, okay? And I need to give it to you. Let's see, there's an example. I'm going to insert another slide here. Okay. So if I look at my Laplace transform table, I would find that we know that the Laplace transform of cosine omega t is equal to s over s squared plus omega squared. Turns out that the Laplace transform of e to the minus sigma t times cosine omega t looks like this: s plus sigma over s plus sigma squared plus omega squared. Right, so I can see that the denominator of this Laplace transform is the same as what I have in my partial fraction expansion. But if you look, the numerator is not the same, right? Over here I've got just s plus sigma here, and I could have any residual r2 or r3, any residue here. So I need one more transform, and it turns out that's the decaying sine wave. e to the minus sigma t sine omega t is equal to omega over s plus sigma squared plus omega squared. Okay, so what I need to do is I need to make use of both of these Laplace transforms. Okay, so the easiest way for me to explain how to do this is to do an example. So I'm going to write my f of s is equal to 3 over s times s squared plus 2s plus 5. Okay, and I'm going to write it like this: r1 over s plus r2 s plus r3 over s squared plus 2s plus 5. Okay, and this looks a little bit different from the way that I wrote the in the Laplace transforms. I have a term that looks like s plus sigma quantity squared plus omega squared, and so I could note that if I expanded that out, right, I get s plus sigma squared plus omega squared. That's going to be s squared plus 2 sigma s plus sigma squared plus omega squared. And so if I look at the actual denominator that I have, I can see that here I have 2 sigma is equal to 2, so that means that sigma is equal to 1, and sigma squared plus omega squared is equal to 5, and so that gives me omega is equal to square root of 5 minus 1, square root of 4, it's 2, okay? So in other words, I want to write the denominator s squared plus 2s plus 5. I can express it as s plus 1 quantity squared plus 2 squared. And the reason I do this is now I have it in a form that looks like the Laplace transform, s plus sigma quantity squared plus omega squared. Okay, so I know this is going to be my oscillation frequency and this is going to be my decay time. Okay, so R1 is easy. Here, I'll put a little set of bars here. This, okay. So R1 is easy. We just do R1 is going to be equal to S times f of s evaluated at s equals 0. And so I get 3 over s squared plus 2s plus 5 evaluated at s equals 0. So that gives me 3/5. Okay, that's the first residue. And then how do I find R3 and R2? Okay, so there's a little bit of math involved here. Okay, we're going to multiply both sides by the denominator. So I'm going to clear the entire denominator. By multiplying right-hand side and left-hand side by the complete denominator, s times s squared plus 2s plus 5. Okay, and so what I get when I do that, I get 3 on the left-hand side, because there's no denominator there, is equal to R1 times s squared plus 2s plus 5 plus R2 plus, R2s plus R3 times s. Okay? And now what I'm going to do is collect powers of s. So in other words, like the s squared terms, the s terms, s to the 1th and s to the 0th terms. Okay, so I have an R1 times s squared, and I have an R2 s squared. Okay, and then in terms of things that are multiplying s, I got R2R1, and I have an R3. So I get 3. Okay, and then the s to the 0, right, so there's basically no s's here. I've got 5R1, and I guess that's it, and minus 3, right, when I shift it over. 5R1 minus 3 equals 0. Okay, so this is now a polynomial in S. And so when I'm trying to find this, so I'm setting this thing equal to 0, it must be that this holds for all values of s, and so it means that each of these terms that are in parentheses here must actually be equal to 0. Okay, so this holds. So it ends up that 5r1 minus 3 is equal to 0, right? Which is r1 is equal to 3/5. We already do that. And 2r1 plus r3 is equal to 0. And so r3 is equal to minus 2 times r1, so it's minus 6/5. And then the last one is r1 plus r2 is equal to 0. And so it says that r2 is equal to minus r1, so minus 3/5. Okay? So now we found all the residues. And so I'm going to write it out. F of s is equal to 3/5 times 1 over s plus minus 3/5 s minus, whoops, not plus, minus 6/5 over s squared plus 1 plus 1 squared plus 2 squared is the way I'm going to write it, okay? And, well, I could factor out the 3/5 just to make it a little bit simpler. 3/5 times 1 over s plus, so I'm going to take the negative sign here, minus s plus 2 over s plus 1 squared plus 2 squared. Okay, now here is the last little trick here. What I've got to do is I've got to, in order to use the transforms that I have, I've got to get them set up so that I have something that looks like s plus sigma and something that just looks like an omega like this. It could be a constant times omega. Okay, so in this case, I could write this as s plus 2 over s plus 1 squared plus 2 squared. Well, that's equal to s plus 1 over s plus 1 squared plus 2 squared plus 1, right? So I just, s plus 2 is equal to s plus 1 plus 1, right? That's all I did. S plus 1 squared plus 2 squared. So this guy is already in the form that I need it to be. And just, I'm going to do one little tweak here. This is 1/2 times 2, okay? And the reason I did that is now these are both in the form that I can take the inverse Laplace transform. So I'm going to write it like this. Laplace inverse of this stuff above is going to be equal to, well, it's just 1 times e to the minus sigma, sorry, the sigma is 1 here, e to the minus t cosine 2t plus 1/2, right? There's a 1/2 here, e to the minus t sine of 2t, okay? So I took care of what I just did. I'll put a little bar here. So I'm only taking care of this part here, okay? Only dealing with the second part of it. And so the first part, well, that one's easy because it's just a unit step. So I can write the full solution down at the bottom. F of t is equal to 3/5 times 1 minus e to the minus sigma, or so e to the minus t cosine 2t minus 1/2 e to the minus t sine of 2t, and the whole thing multiplied by the unit step. Okay, and that's all for this time. So see you on Monday.